Welcome to A-Level and AP Physics. In today's lesson, we will discuss past paper questions on gravitational field, thermal physics, and simple harmonic motion from October-November 2022, paper 4, variant 1. As always we do, we will discuss these questions in detail so you can improve your conceptual understanding of these topics and also you can have better understanding of these questions. Let's study together, let's improve together. In today's class, we will discuss paper 4.1 from October-November 2022 and total time for this exam is 2 hours and total mark for this paper is 100 and you need to answer all questions on this paper. If you go to the second page of this exam paper, on the second page you can see some data is given to you. And this data is very important maybe in your exam. During your exam, you will need some of these constants for some calculations. So if you need value of any constant in your exam, you can come to this paper and you can find values of constants. And if you go to the next page, on the next page, you can see some important formulae are given to you. Here you can see all these formulae. These are for AS physics, but maybe you will need some of them for some calculations in your A2 physics as well, means for some basic calculations. And these all formulae you need for A2 physics, but these are not all the formulae you need for A2 physics. These are some basic formulae are given to you. So rest of the formulae you have to remember by yourself or you need to understand how to derive those formulae. So in the exam, if you need any formulae but you have forgotten that or you are not very clear about that formula, you can come to this page and you can recheck. So it's very important to understand that some data and formulae are given to you in this paper. So if you need any of them, you can come to this page and you can find formulae or you can find data, means values of constants. For question number 1, part A, we need to state the equation for the gravitational force between 2 point masses M1 and M2 that are separated by a distance small r. We also need to state the meaning of any other symbols we choose, mean other than given symbols in the question. We have to state that symbol as well, state the meaning of that symbol. So in this case, we have point masses, we have M1, we have another point mass that is M2 and the separation between these 2 point masses is given to us and the separation is equal to small r. We need to write down equation for gravitational force. Gravitational force simply will be equal to the capital G times M1 times M2 divided by the separation between them, square of separation, or simply you can say square of distance between point masses. In this case, we have the symbols. These symbols are given to us. This is given, M1 is given, M2 is given, R is given. But this symbol was not given in the question. So simply we need to write down what is G. G is gravitational constant. So simply we can say G is gravitational constant. So this is gravitational constant. So if you write down this, you will get 2 marks. For part B, it is given to us a satellite is in a circular orbit of radius capital R around a planet of mass capital M. Show that time period T of the orbit is given by this, where K is a constant that depends on the value of capital M. Explain your reasoning. This is a typical question about Newton's law of gravitation. But the best way to answer this question is always sketch. So in this case, we have a planet and the mass of the planet is capital M. So this is mass of the planet. Then we have satellite and mass of the satellite is small m. And the orbital radius of satellite is given, means the distance between centers of planet and satellite is given. That is equal to capital R. And this satellite is orbiting around the planet. So this is orbiting around the planet. And we need to find out expression for the time period of satellite. So in this case, as this satellite is orbiting in a circle, so its orbit is circular, so the gravitational force in this case is providing the centripetal force. I mean, the centripetal force is provided by the gravitational force. So it's very important to write down in this case, gravitational force provides centripetal force. Centripetal force is not a force by itself. Centripetal force is just a fancy name for resultant force. So we have to write down gravitational force provides centripetal force. Centripetal force. This has 1 mark. So it's very important to write down. Gravitational force provides centripetal force. Gravitational force is equal to G capital M small m over R square, and this one has to be equal to mv square divided by capital R. R is the distance between centers of satellite and the planet, and this R is the radius of the circle. Sometimes these two are not equal, so you have to be very clear about this one. Now for this question we need to find the relationship between T, but T is not here. So first of all we can simplify. We can cancel this m with this m. This R we can cancel with this. Now if we write down, we have only G capital M divided by R on one side, and we have V square on the other side. But V is the orbital speed. V is the orbital speed, and orbital speed is equal to 2 pi R divided by T. So we can replace this V square with 2 pi R divided by T square of this. Now if we simplify this one, we will get this is equal to 4 pi square R square divided by T square, and here we have G capital M divided by R. Now we can further simplify. We need T square on one side, so we can write down G capital M T square. Simply just cross multiply, means cross multiply. So we are just doing cross multiplication in this case, just cross multiply. So we will get here, this will be 4 pi square, and this one will be R cube. This will be R cube. So we need to find out T square. So T square we have to make the subject. So here we have 4 pi square divided by G capital M, and here we have R cube. So in this case, this is equal to K, because T square is equal to K times R cube. So this is K and this over R cube. Simply finally we can say that T square is equal to K times R cube. So this is what question was asking you to derive. So if you have derived this one, you will get 3 marks, because this question has total 3 marks. For part C, it is given to us a satellite is in a circular orbit around the Earth with a period of 24 hours. The mass of the Earth is given. We need to calculate radius of the orbit. So this is very similar question as we have done in the last part. So we can imagine this is our planet, and the mass of the planet is capital M, and we have satellite here, and mass of the satellite is small m. So this is orbiting in this circular orbit. And the force on this one, the centripetal force in this case, is provided by gravitational force. So this is F. So in this case, we need to calculate the radius of the orbit. Means we have to calculate value of this R. We can say this is capital R. And we have already derived in part B that T square is equal to 4 pi square divided by GM divided by G capital M times R cube. So in this case, we need to find out value of R cube. So we can rearrange this one, and so we can write on R cube in this case will be equal to T square times GM divided by 4 pi square. So we need to find out value of R. So we have to take cube root on both sides. So we will have T square, this will be GM divided by 4 pi square. We have to take cube root of this one, 1 by 3. Now simply we need to plug in values, and we can find out value of R. In this case, value of T is given, that is equal to 24 hours. So we have to convert this one into seconds, because we are using SI based units. So we need to convert this one into seconds. 24 hours. 1 hour has 60 minutes and 1 minute has 60 seconds. So we have to take the square of this. G is a constant, and value of G is 6.67 times 10 to minus 11. And the mass of the planet we have, that is equal to 6.0 times 10 to 24. And this is divided by 4 pi square, 4 pi square. And we need to take cube root of this one. If we take cube root of this one, our final answer will be equal to 4.2 times 10 to 7 meters. And this is our final answer up to 2SF. So why we are using 2SF in this case? Because the given data is up to 2SF formula. You can see this one has 2SF and this also has 2SF. So we have to use the least number of SF in given data. So the answer for this question is this. So this question will have 2 marks. 1 mark if you have plugged in these values and you have used right formula. you will get 1 C mark. And this one will be the answer mark. If you have got the right answer, you will get 2 marks for this question. For the second part, we need to state 2 other conditions that must be met for the orbit to be geostationary. Other 2 conditions, because in part 1, one condition was given, that was 24 hours. Means the time period has to be 24 hours, because our planet also complete one rotation about its own axis in 24 hours. So the time period of this geostationary satellite also has to be equal to 24 hours. Geostationary satellite simply means that, imagine that if a person is standing on the surface of our planet and geostationary satellite is here. If this is a geostationary satellite, it has to stay always above the head of this person. Means always above the same point on the surface of our planet. So that satellite will be geostationary satellite. And that is only possible if it is above equator. So the one condition is satellite has to be above equator. And the second condition is that its direction of rotation has to be the same as direction of rotation of the planet about its own axis. And that is from west to east. So this satellite has to also orbit from west to east. West to east. So these 2 conditions we can write down. So for the answer of this question, simply you can write on these 2 conditions. You can say first one, orbit must be above equator, and second one from west to east. So if you write on these 2 points, you will get 2 marks, and this one has to be B mark, and this one also has to be B mark. For our second question, part A, we need to state 2 other physical properties of materials apart from the density of a liquid that can be used for measuring temperature. Physical properties of materials. Actually, question is asking you about thermometric properties. So how we can link the physical properties of material with temperature? So that property we call is thermometric property. Means a property of material that changes with temperature we call is thermometric properties. And thermometric properties we have, for example, resistance of a metal. Because resistance of a metal, this one changes with temperature. So we can also use resistance of a metal to make a thermometer. We can also use volume of a gas. Volume of a gas at constant pressure. Volume of a gas at constant pressure we can also use. Means if the pressure is constant, then the volume will change with temperature, and we can use this property to make a thermometer. And also we can use EMF of a thermocouple. EMF of a thermocouple, because EMF of a thermocouple that depends on temperature. So we can also say EMF of a thermocouple. So these properties we can state in our answer. So any 2 you have to state. Even we can also use color as a thermometric property. That can be another one. So in this case, simply you can write down these 2 properties. You can say resistance of a metal and volume of a gas at constant pressure. So these 2 thermometric properties we can state. For part B, it is given to us the thermometer is initially at 23.0 degrees Celsius as shown in figure 2.1. It is used to measure the temperature of an insulated beaker of water that is at 37.4 degrees Celsius. The bulb of the thermometer is inserted into the water and the water is stirred until the reading on the thermometer becomes steady. The mass of the water is given to us. The mass of the mercury is given. The specific heat capacity of water is given, and the specific heat capacity of mercury is given as well. And it is also given to us that glass of the thermometer and the beaker containing the water can be considered to have negligible heat capacity. So it simply means that we can ignore the heat gained by beaker and the heat gained by glass of the thermometer. So then simply we left mercury and water. And we need to calculate for part 1 up to 3 significant figures the final steady temperature indicated by the thermometer in the water. Temperature of the thermometer. So in this case we have liquid and we have mercury. So the liquid in this case will lose heat, thermal energy, and mercury will gain. So simply we can say in this case Q lost by water. Q lost by water, this one will be equal to Q gained by mercury. So we can say Q gained by mercury. So this is just energy conservation gained by mercury. And for the water, so we can simply say this is MW CW times delta TW. This one has to be equal to the mass of the mercury. We can say this is Hg, C of the mercury, C of the mercury. So this is Hg times change in temperature of mercury. Now simply we need to plug in values, but we can simplify further. So we have mass of water, we have C for water, and the final temperature of the water, it will be lower than the initial temperature. So we will take the initial temperature minus final temperature. So this change will be positive. And on this side, we will also do the same thing. So we have mass of mercury, we have C for mercury, and the final temperature of the mercury will be higher than the initial one. So we will take the final temperature. Let's say the final temperature is capital T. So the final temperature of mercury and water will be the same. Minus we have initial temperature of mercury, that is 23.0. So that is 23.0 degrees Celsius. So one thing we need to understand, change in temperature in degrees Celsius is equal to change in temperature in Kelvin. So we no need to convert units. Now simply we need to plug in values. So here we will plug in values and we will find out value of T. And if you look at specific heat capacity, this is given in joules per gram per Kelvin. So it means mass we can use in grams. So always you have to keep an eye on units of specific heat capacity. So this is given in joules per gram. So it means mass you have to use in grams. So for the mass of the water we have is 18.7. So we can write down this is 18.7 grams times C for water. Value of C for water we have 4.18. So this is 4.18. And change in temperature, so we have 37.4 minus capital T. And mass of the mercury we have 6.94. So this is 6.94. And C for mercury we have that is 0.14 joules per gram per Kelvin. You can see if you compare these two C, this C is much bigger than this C. So that point is very important to understand. And the change in temperature will be T minus 23.0. Now simply we need to solve this one for T. If we solve this one for T, our final answer will be equal to 37.2 degrees Celsius. So this is 37.2 degrees Celsius. So simply we can write down T will be equal to 37.2 degrees Celsius, and this is our final answer. For the second part, we need to suggest one change that could be made to the design of the thermometer that would enable it to give a more accurate measurement of temperature. So we need to make change to the thermometer, but in this case it is given to us that initial temperature of the water is equal to 37.4 degrees Celsius. And the temperature measured by a thermometer, that one is equal to 37.2 degrees Celsius. And this is what we have done in part 1. Now we need to change the design of the thermometer so these two values, they get closer to each other. Means we have to increase the value of T. For that purpose, simply we can look at Q lost by water. This one is equal to Q gained by mercury. Q gained. Q lost by water is mass of the water times C of the water, time we have initial temperature of the water minus the final temperature of the water. And this is equal to mass of the mercury. We can say this is mHg, mass of the mercury, and here we have this is C for the mercury, and here we have final temperature of mercury minus the initial temperature of mercury. Now in this case we want to increase this T. To increase this value of T. So if this temperature increase, for example this one, so we will see overall this one will go down. So this value will go down. So this overall heat gained by the water, this one will go. Heat lost by the water, this will go down. So it also means that overall this will go down. This one also will go down. Overall this one has to go down because heat lost has go down is lower, so the heat gain also has to be lower. But in this case, when this temperature is higher, this temperature also will be higher because this is the equilibrium temperature. So in this case, we have to decrease the mass of the mercury. So we have two options. One option, we can decrease the mass of the mercury. So this is one option. The second option, we can take an other liquid. So let me use different color. We can take another liquid. Let's say we have another liquid that has mass m, and mass m is equal to mass of the mercury, and another liquid has C different, value of C is different, and here we have this is temperature, final temperature, minus we have the initial temperature of thermometer, initial temperature of the liquid inside thermometer. So in this case, we can keep the same mass, means the mass of the new liquid can be the same as the mass of the mercury, but we can decrease the value of C of new liquid. So if the new liquid, it has lower specific heat capacity, it means its temperature will increase more with the same amount of heat gain. So you can also understand in a simpler way this one, C is equal to Q over M times delta T. So C is equal to Q over M times delta T. So if we lower this C, so this Q also will be lower. If we are talking about the same mass, if we are talking about the same change in temperature. So if the C is lower, it means the liquid will absorb less amount of heat, less amount of thermal energy for the same rise in temperature. So in that case, we can increase this value of T. So we can increase this value of T. So liquid will absorb smaller amount of thermal energy and the increase in temperature will be higher if the C is lower. So you can also write on this one like this. Delta T will be equal to Q over M times C. If the C is lower, so it means Q also has to be lower. Q has to be lower. Or simply, you can also understand in a little bit different way. So we can say if C, for example, C, if we use the same amount of heat gain, if the C is lower, change in temperature will be higher. So if the change in temperature is higher, it means that this temperature will be close to actual value of temperature. So we can make two changes. One change, we can decrease the mass of the liquid inside the thermometer. Second one, we can change the liquid in thermometer and we can replace with a liquid which has lower specific heat capacity. So we can make two changes. So in your answer, you can mention about these two changes. So one change you can say is use another liquid with lower specific heat capacity, or we can use a smaller mass of mercury to get more accurate value of temperature. For part C1, we need to explain why the thermometer in figure 2.1 does not provide a direct measurement of thermodynamic temperature. Thermodynamic temperature means that temperature in Kelvin. So we cannot measure temperature directly in Kelvin using this thermometer because this thermometer is starting from minus 10 degrees Celsius. Minus 10 degrees Celsius. And minus 10 degrees Celsius is not absolute zero. Means it is not 0 Kelvin. This is not equal to 0 Kelvin. So this is first thing we can say. This is not equal to 0 Kelvin. So that's the reason it cannot measure thermodynamic temperature directly. Means temperature in Kelvin. Why it cannot? The reason is that mercury at 0 Kelvin, at absolute zero, will be just frozen. Because at absolute zero, atoms, even they stop vibrating. They have no kinetic energy at all. That theoretical, hypothetical temperature we call is absolute zero. So it depends on substance as well. So we don't have any substance which has temperature that is 0 Kelvin and substance is not in frozen form. Because 0 Kelvin is just hypothetical temperature. So we cannot have a thermometer that starts with 0 Kelvin. But we can convert temperature from degrees Celsius into Kelvin. So one is real substance. And other thing you can say 0 degrees Celsius or you can say minus 10 degrees Celsius is not absolute zero. So we cannot measure thermodynamic temperature directly with this thermometer. So we can write on 2 points for this. So one point you can say It depends on properties of a real substance. Second, 0 degrees Celsius is not absolute zero. So you will get 2 marks. Now let's go to the second part. For the second part, it is given to us that thermodynamic temperature T may be determined by the behavior of a type of substance for which T is proportional to the product of pressure and volume. T is proportional to the product of pressure and volume. So this is talking about ideal gas, means PV. This is equal to nRT. So from here we can see PV is directly proportional to T. So this temperature has to be in Kelvin. So this is proportional to T. So it's asking us state the name of this type of substance in which the product of P and V is directly proportional to T temperature in Kelvin. And that is ideal gas. So that is ideal gas. Because this equation is for ideal gases only. So simply you have to write on ideal gas. For our third question, it is given to us an object is suspended from a spring that is attached to a fixed point as shown in figure 3.1. The object oscillates vertically with simple harmonic motion about its equilibrium position. For part A, we need to state the defining equation for simple harmonic motion, and also we need to identify the meaning of each of the symbols used to represent physical quantities. So first of all, we need to write down the defining equation. Defining equation for simple harmonic motion is A is equal to minus omega square x. And this equation is very important for you to understand because they will ask you a lot of questions about this one. If there is any question in the exam about simple harmonic motion, means they will ask you about this equation. So you have to be very clear about this one. So in this equation, we have A. A is the acceleration. So A simply we can say A is the acceleration. So you can write down A is acceleration. And X here is the displacement from equilibrium. So we can say X is displacement from equilibrium. So X is displacement from equilibrium. We can say equilibrium position. So this is omega. Omega is the angular frequency. So if you simply write on this much, you will get 2 marks. So this is the angular frequency. Omega is angular frequency. So that's all what you need to write. For part B, it is given to us the variation with displacement x from the equilibrium position of the velocity v of the object is shown in figure 3.2. The variation with x of the potential energy of the oscillations of the object is shown in figure 3.3. We have to use figure 3.2 and figure 3.3 to determine the amplitude of the oscillations. The amplitude means the maximum displacement. So if you look at this figure, the maximum displacement is equal to 0.12 meters. And also you can see from here, the maximum displacement is equal to 0.12, means where the potential energy is maximum. And here where the speed is equal to 0. So simply you can say the maximum amplitude, maximum displacement, that is equal to amplitude, and the value of the amplitude is 0.12. For the second part, we need to show that angular frequency of the oscillations is 1.7 radians per second. But we understand that speed of the oscillator is linked with displacement, means V is equal to omega times A square, this is the amplitude, minus displacement square. And the speed is maximum, V is maximum, speed is maximum when x is equal to 0, means when the displacement is equal to 0, speed is maximum. So simply we can write on from here V max, this will be equal to omega times a square minus 0. So from here we can say V max simply is equal to a times omega, and value of V max we can read from here. V max is equal to 0.2 meters per second, and value of A we have already determined, means the maximum displacement, that is equal to 0.12, and here we have value of omega. So from here we can calculate value of omega, and value of omega will be equal to 1.7 radians per second. So this is our final answer. So this is how you can calculate value of angular frequency. For our third part, we need to determine the mass capital M of the object. But we can find the maximum value of the potential energy from this figure. And also we have value of amplitude, means the maximum displacement. So simply we can say in this case potential energy maximum, or we can say EPE maximum. This is equal to the total energy of this spring mass system. And this is equal to 1/2 M, capital M, mass of the object hanging with the spring, times omega square times amplitude square. We need to find out value of M. We have value of EPE that you can read from here, and that is equal to 0.050 joules. We have 1/2 M we need to find out. Value of omega we have already calculated in the second part. That was equal to 1.7, but you no need to use 1.7 here. You have to use answer before rounding off. So we will be using here 1.67. So this is the accurate answer. Accurate value for omega up to 3 SF. So you have to use more than 2 SF in this case. So we will be using before rounding off. Means 1 or 2 SF greater than the final answer. So we are using 1.67. This is value of omega. So this is square times amplitude. Amplitude is 0.12 and square of this one. Now if we solve this one for M, we can find out value of mass. And value of mass in this case will be equal to 2.5 kg up to 2 SF. Because the given data, the least number of SF we have, 2 SF. And this also has 2 SF. So this is our final answer for the mass. So simply we can say this is equal to 2.5 kgs. For part C, it is given to us the oscillations of the object are now likely damped. We need to state what is meant by damping. Damping is simply loss of energy of the system due to resistive forces. So let's try to sketch this one. So because sketch is very important. So damping, let's say we have X, this is on Y-axis, and let's say we have time on Y-axis. So likely damped means that amplitude is decreasing gradually. So you will see amplitude decreasing gradually like this. So this means it's likely damped. So in this case, amplitude is decreasing exponentially gradually. So amplitude is decreasing. So this is light damping. So simply you can say loss of energy of the system due to resistive forces. So if you write on this one, you will get 2 marks. 1 mark for writing loss of total energy of the system, and the second mark due to resistive forces. So you will get 2 marks. For the second part, we need to assume that damping does not change the angular frequency of the oscillation. So it simply means that omega in this case is constant. Omega is constant. On figure 3.2, we need to sketch the variation with x of v when the amplitude of oscillations is this one. But if you look at the initial value of the amplitude, that is equal to 0.12. So if we compare these two together, we can simply say initial amplitude is equal to 0.12 and the new amplitude. So this is in meters. And the new amplitude is equal to 0.060 meters. So simply we can say A new in this case is equal to A naught by 2. We also understand V max. V max is equal to A times omega. In this case, omega is constant, but A become half. So we can say the new value of V max, this will be equal to A naught by 2. So we have this is A naught by 2 times omega. So the new value will be equal to 0.2, means the maximum value divided by 2. So from here we can find out new value will be equal to 0.1. So this is new value of V max. So this is new value of V max. Because amplitude become half, so it means V max also become half because omega angular frequency, this is constant. So now simply we can mark these values. The amplitude is 0.06. So this will be halfway between 0.04 and 0.08. So we have 1, 2, 3, 4, 5. So this is value of amplitude. And the maximum value of the velocity will be this one. So we can little bit clear this. So this will be the maximum value of speed. And also we can mark here 1, 2, 3, 4, 5. So this is. and maximum value of velocity is this one. Now simply we need to connect these points. So let me show you how you can do in a beautiful way. So this is simply how you can sketch. So this is our final answer. So this is how you need to sketch this curve. If you sketch like this, you will get 2 marks for this question. 2 marks, because the total marks for this question are 2. So these points are important. This point is very important. When velocity is 0, displacement has to be equal to 0.06, and when x is 0, maximum value of v has to be equal to 0.1, and when displacement is equal to 0.06, v has to be 0, and when x is 0, v has to be equal to 0.1. So if you draw this, you will get 2 marks. I hope these questions are clear to you. So we have done 3 questions from this paper, and the remaining questions are coming very soon. I'll be uploading by tomorrow. So in next 2 or 3 days, I will try to finish this paper. And if you found this video helpful, and if you like this video, please like and subscribe channel, because your encouragement is important. So with your encouragement, I'll be making more and more videos, and we will study physics together, and we will improve together. I'll see you next video. And also, if you have any questions, please just leave your questions in comments, and I'll try to answer as soon as possible. Welcome to A-Level and EP Physics. In today's lesson, we will discuss past paper questions on electric field, capacitance, and Hall voltage from October-November 2022, paper 4, variant 1. As always we do, we will discuss these questions in detail so you can improve your conceptual understanding of these topics, and also you can have better understanding of these questions. Let's study together, let's improve together. For question number 4, part A, we need to state what is indicated by direction of an electric field line. Let's try to understand this one with one very simple example. Imagine that we have a positive charge. So this one is a positive charge. And if we draw electric field lines around this positive charge, we will draw arrows pointing away from this positive charge. Arrows pointing away. Now we need to understand, why do we draw arrows pointing away from positive charge? There must be some reason behind that. The reason is that these lines are telling us direction of force on positive point charge. So if we imagine a positive point charge is placed at this point, so this positive point charge will experience force away from this positive source charge. So these lines are simply telling us, if you place a positive charge in electric field of positive point charge, there will be force on positive test charge away from the positive point charge. So these lines simply tells us direction of force on positive charge. So simply we can say lines indicate direction of force on positive point charge. Lines indicate direction of force on positive test charge. Positive test charge. So test charge always we take positive by convention. We can also understand this one with the help of negative charge. Now imagine that we have a negative point charge. So this is negative point charge. If we draw electric field around this one, and we draw these electric field lines, we will draw arrows in this case pointing towards this negative point charge. So we will draw arrow like this. So this is always we do. And this question is simply asking you the reason behind that. Now in this case also imagine that if we place a positive charge here, let's say we place positive test charge at this point. So the force on this positive charge will be through the negative charge, means towards negative charge. So if we place a positive test charge here, so this is test charge, means this is positive. So the force on this one will be towards negative point charge. So field line simply tells us direction of force on positive test charge. So simply in this case, you can write down these electric field lines. Field lines indicate direction of force. So you will get 1 point. So field lines are telling us direction of force. You will get 1 mark, and this is big mark. If you have written on positive charge, you will get another mark, and this one will be B mark. So this is how these 2 marks will be awarded to you. For part B, it is given to us figure 4.1 shows a pair of parallel metal plates with a potential difference of 2400 volts between them. The plates are separated by a distance of 4.6 centimeters. The plates are in a vacuum. For part B1 on figure 4.1, we need to draw 5 lines to represent the electric field in the region between the plates. So first thing in this case, we need to understand the electric field between the plates. Electric field will be uniform electric field. So simply we can say uniform electric field. Uniform. So in case of parallel metal plates, electric field between the plates will be uniform electric field. Uniform. And if the field is uniform electric field, then you need to understand separation between lines. Separation between lines should be same. Separation between lines, same, simply you can say. So lines, separation between 2 lines, any 2 lines has to be the same. So separation between lines, same. So this is one thing you need to consider. And the second thing you need to understand is that electric field lines point from positive plate to negative plate. So direction of electric field lines have to be from the positive plate, more positive plate, to less positive plate. So we can say more positive plate to less positive plate. In this case, this plate is more positive. Not only positive to negative, so simply it means is from more positive to less positive plate. Less positive, or simply we say positive to negative. So these are the points you need to understand. If you have understanding of these points, then simply we can draw our electric field lines. So we can start with one electric field line here. Another one can be at this point. Another one can be at this point. Another one can be at this point. And other one can be like this. So these can be the possible electric field lines. So question is asking you to draw only 5, but at least you have to draw the 5, but you can draw more than 5 as well. So if I just want to draw only 5, so this is how I can draw. So these are 2 electric field lines, and the third one we can draw here, fourth one we can draw here, and the fifth one we can draw here. 5, even you can draw more than 5, at least 5 you have to draw. And in this case, the separation between the lines have to be the same. So this separation is important. You have to consider this separation. So this separation between the lines have to be almost same. So it has to be same. It's a little bit more, but it has to be almost same. So this separation has to be almost same between the lines. So if you draw this one, you will get in this case 3 marks. So 3 marks will be awarded. For the second part, we need to calculate the electric field between the plates. And we have already discussed that electric field between these 2 parallel plates is uniform. So simply we can say in this case E, this is equal to the potential difference between 2 points divided by the distance between those 2 points. You can take any 2 points, but in this case we will be taking 1 point here on the positive plate, more positive plate, and we will be taking 1 point on the less negative plate, because we have value of separation between these 2 plates. And also we have the potential difference between these 2 plates. Potential difference is equal to 2400 volts. And the separation between plates, between these 2 points, that is equal to 4.6 centimeters, means 10 to minus 2. Now, if we solve this one, our final answer will be 5.2 times 10 to 4 newtons per coulomb. Or you can say volts per meter. Newton per coulomb, or you can say volts per meter. These are the same units. So, in this case, we're using 2SF. The reason is that in the raw data, in the given data, the least number of SF, we have 2SF. So we are also using 2SF in the final answer. For part C, it is given to us a moving proton enters the region between the plates from the left as shown in figure 4.2. For part C1, it is given to us the proton is deflected by the electric field. On figure 4.2, draw a line to show the path of the proton as it moves through and out of the region of the electric field. So in this case, when this proton will enter the electric field, it will experience electric force. But in this case, we will ignore the effects of gravity. We will only consider electric force because gravity is much smaller than the electric force in the electric field. So that's the reason we will ignore effects of gravity. Now in this case, it is given to us the upper plate. This is more positive, so we can mark here with positive points. Mean this is more positive, and this plate is less positive. So less positive plate we can just treat as a negative plate for simplicity. So this plate is negative, relatively negative as compared with this one. So in this case, there will be repulsive force due to positive plate, due to these positive charges on this proton, so that force will be down. And also there will be attractive force due to negative plate, so that force also down. So the resultant force, simply we can say electric force will be in downward direction. So this is direction of electric force. And proton in this case is moving horizontally, and electric force is acting downwards always in one direction, always in one direction. So this is very similar to projectile. So if a projectile is projected horizontally in a gravitational field, so it will follow parabolic path like this, because gravity at any point is just acting in one direction. And the same is true in this case, because electric force is always pointing down in this case. So the path of this one inside the field, it has to be parabolic like this, and outside of the field this will be just a straight line. So simply we can draw a straight line, so it will be a straight line. So this is the path of proton in the field and outside of the field. Outside of the field, simply you can draw a straight line. Why it's like this? Because electric force is just acting in one direction all the time. So this path is parabolic. So this one has to be parabolic path. So if you draw this one, you will get 2 marks. And this one has to be straight line. We are ignoring effects of gravity. So this one has to be a straight line. Let me just draw a proper straight line. So when the charge is here at this point, line after that has to be a straight line. So we can use dotted lines here. So this one has to be straight line like this. So this is how you can draw. For the second part, it is given to us a helium nucleus now enters the region of the electric field along the same initial path as the proton traveling at the same initial speed. State and explain how the final speed of the helium nucleus compares with the final speed of the proton after leaving the region of the electric field. Means simply at this point we have to compare the speed of proton with speed of helium nucleus. So we have 2 particles now. One particle is proton and other particle is helium nucleus. So simply first of all we can compare these two. First of all, helium nucleus, proton has charge plus E and the helium nucleus has charge plus 2E, and the mass of proton is equal to 1U and the mass of helium nucleus is equal to 4U. Atomic mass unit, U is atomic mass unit. So the mass of helium nucleus is 4 times greater than proton, than mass of proton, and the charge on helium nucleus is 2 times greater than charge on proton. And we need to compare their final speeds. Now the first thing we need to understand, we have already discussed that in this case force acting on positive charge is always downwards. So it simply means that the particle, the positive charge in this field will be accelerating vertically downwards. But horizontal component of the speed, it will not change. It's just like projectile. So the horizontal component of velocity will not change, but vertically it will accelerate. So the vertical component of the velocity will increase. So we can calculate first of all vertical acceleration. For the helium nucleus, we can simply write down F net. This is equal to ma. Then we can compare this one with proton as well. F net is equal to ma, and F net in this case is only due to electrical force. So we can say EQ, and this is equal to ma. As I said before, in this case we will ignore gravitational force because gravitational force in the electric field is negligible as compared with electrical force. So that's the reason we are simply saying EQ is equal to ma. So from here we can find out value of acceleration, means vertical acceleration. So this is equal to EQ divided by m. In this case electric field is the same, so both particles, they are in the same electric field. So we can say electric field is the same. Now if we say the charge on proton, let's say charge on proton is Q. So the charge on helium nucleus will be +2. If we say the mass of proton is m, so the mass of helium nucleus will be equal to 4m. So in this case, simply we can say this is E. So for helium nucleus, this charge will be 2q and the mass of helium nucleus is 4m. So we can find out from here that this one will be equal to EQ divided by 2m. EQ divided by 2m. So simply it means that acceleration of helium nucleus, this will be half. So this is A, means this is the acceleration of proton, divided by EQ by m, we are saying this is acceleration of the proton. So this will be divided by 2. So from here we have found that acceleration of the helium nucleus, this one is equal to acceleration of the proton divided by 2, means the acceleration is half. If acceleration of helium nucleus is half and we look at the final vertical speed, so final vertical speed will be equal to VV U vertical plus AT, and these two particles, they will spend the same amount of time in the field because the horizontal speed is the same. So time in this case is the same, and initial vertical speed is equal to 0. And if acceleration is half, so it means the speed of the helium nucleus will be half. So we will say the vertical speed of helium nucleus, this will be equal to half of vertical speed of proton. So this is we can find out. So in this case, simply the vertical component of velocity of helium nucleus will be half of vertical component of velocity of proton. So at this point, this velocity will have two components. One is the horizontal component, they have the same horizontal component, and one is the vertical component. This is V vertical, and the velocity V at this point, V will be equal to V square plus Vh square. So as vertical component of velocity of helium nucleus is lower, so it means the final speed of helium nucleus also will be lower than the speed of proton at this point. So if we have understanding of these points, we can write down our final answer. So in this case, these points are important. One thing you need to say, acceleration of helium nucleus is lower than acceleration of proton, and both particles, they have the same horizontal component of velocity, because horizontal component of velocity will not change in this case. And also you can say the vertical component of velocity of helium nucleus is also half of vertical component of velocity of proton. So the final velocity of helium nucleus will be lower than the final velocity. If we are talking about magnitude, you can say the final speed will be lower for helium. So these points you need to mention in your answer. This is one point, and this one is the second point. This one is third point. And also you have to compare charges and the masses. So you also have to compare this one. So this thing you also need to compare. And after this comparison, you can write down your final beautiful answer. Now let me show you the answer, how you can write down proper answer. So this is how you can write down a proper answer. In the answer, you can talk about helium nucleus. First of all, the comparison. Helium nucleus has double the charge and 4 times the mass. Velocity parallel to the plates remains same, means the horizontal component of velocity remains same because there is no force along horizontal. Electrical force is only acting along vertical, like gravity. Acceleration perpendicular to the plate smaller for helium, so we have seen this one here. So final speed is lower for helium. It's a beautiful question. So if once it is not clear to you, you can do this question again by yourself and then watch this video again. It will make very clear sense to you. For question number 5, it is given to us the two-way switch S is initially at position X. Initially it is at position X. So in this case we have power supply and we have a capacitor. So capacitor will be fully charged after a few seconds. Capacitor will be fully charged. So this is first thing we need to understand. Then it is given to us at time t is equal to 0, switch S is moved to position 5. So it is moved to position 5. So in this case we have the capacitor in this circuit. right? And we have the wire. So capacitor in this case will discharge. So simply we can say capacitor will discharge. For this discharging circuit, for part A1, we need to find out what is initial value of Q naught at time t is equal to 0. Initial value of Q means Q naught. Q naught is equal to the total charge stored on the capacitor. And total charge stored on the capacitor will be equal to C times V. And in this case, we have the value of C. Capacitance of the capacitor is given, that is 470 microfarad. And also we have value of V, that is equal to 24 volts. And if we solve this one, our final answer will be equal to 0.011 coulombs up to 2SF. So this is our final answer because the data given to us has least number of SF, that is equal to 2SF. So the final answer also should have least number of SF. So the final answer for this one is 0.011 coulomb. So this is our final answer. This question has 2 marks. So the 1 mark in this case will be for writing the formula, and you need to plug in values, and the second mark will be the answer mark. If you got the right answer, you will get 2 marks. If your answer is wrong, you will get 1 C mark if you have written formula and you have plugged in these values. So just basic question asking you Q at T is equal to 0 means the total charge stored on the capacitor. For the second part, we need to calculate current I naught in wire P at time T is equal to 0. So we need to calculate value of current. Means this is the value of current, that is maximum value. So simple question is asking you to calculate I max. So how we can calculate I max? I max in this case will be equal to the potential difference, initial potential difference across the capacitor divided by resistance in the discharging circuit. So initial value of potential difference across the capacitor, this one will be equal to the EMF of the power supply. So simply we will say this is equal to 24 volts divided by resistance in the discharging circuit. So the resistance is 5.6 kilo ohms, means 10 to 30. If we solve this one, our final answer will be equal to 4.3 times 10 to minus 30 amps. So this is the maximum value of current. And current with time, then it will decrease. 4.3 times 10 to minus 30. So this point is very important because initially when we move this switch from X to Y, the potential difference across the capacitor is equal to potential difference across terminals of the power supply. So across power supply means this is equal to EMF of the power supply. So this is how you can answer. For the next part, we need to calculate the time constant tau of the discharging circuit. So simply we need to calculate value of tau, and tau is equal to R times C, and R is the resistance in the discharging circuit. So resistance of discharging circuit. So we can say resistance of discharging circuit. Very important point. Sometimes they can make this one a bit tricky for you. So you need to understand what is this R. Resistance of discharging circuit. So in this case, the resistance of discharging circuit is equal to this. So we have 5.6 times 10 to 30 ohms, and the capacitance of the capacitor, that is equal to 470 times 10 to minus 6. And if we simply multiply this one, our final answer will be equal to 2.6 seconds. So the final answer is 2.6 seconds. And this question has 2 marks. So the 1 mark for this one will be for writing this formula and plugging these values. That mark will be C1, and the final mark will be answer mark. And for this question, there is only 1 mark, so this will be only answer mark. For part 4 on figure 5.2, we need to sketch a line to show the variation with T of the current I in wire P as the capacitor discharges. So this question is about discharging of capacitor, and in your syllabus you also need to understand only discharging of capacitor because charging of capacitor is not part of your syllabus. And for discharging of capacitor, we need to understand how current will change. I as a function of time, this is equal to I naught, means I maximum, times e to the power of minus t over RC. Now we also need to understand when I will approach 0. I will approach 0 if t approaches infinity. It simply means that our graph will not touch t-axis. So we will say graph does not touch t-axis. Does not touch t-axis. Or simply we can say there is asymptote. So in this case, this is how you can sketch the graph. This has to be exponential decay, but it should not touch t-axis. So this is how you can sketch. If you sketch this one, you will get 2 marks. One, its gradient has to be negative and decreasing gradient. And second, it should not touch t-axis. So if you sketch graph like this, you will get 2 marks. For part B1, we need to explain why there is an induced EMF across wire Q during the discharge of the capacitor. So first of all, we need to understand when we move this switch from X to Y, this capacitor will start discharging. And when this capacitor is discharging, current in the circuit, in this discharging circuit, or simply you can say current in this wire, this will decrease exponentially with time. So here we have time. So this will decrease exponentially with time, means it will decrease like this. So as current in this wire is decreasing and there is current in the wire, so there is a magnetic field around this wire. So this wire Q is placed inside changing magnetic field of wire P. So it means there is change in the magnetic flux. As there is a change in the magnetic flux, so it means there will be EMF induced in wire Q. Because wire Q is placed inside a changing magnetic field, so there is a change in the magnetic flux. Or you can simply say is placed inside a decreasing magnetic field. So there is a change in the magnetic field, so there is a change in magnetic flux. So there will be EMF induced. So as current is changing, so simply we can also say as current in this wire is changing, there is a change in magnetic field. And as there is a change in magnetic field, it means that there will be change in flux. As there is a change in the flux, there will be EMF induced in wire Q. So EMF will be induced in wire Q. If you have understanding of these points, so simply you can write down your answer. So the main point you need to understand in this case is that as current in this wire is decreasing, so the magnetic field around wire is also decreasing. So the wire Q is placed inside changing magnetic field. So as the wire is inside a changing magnetic field, so there will be EMF induced in wire Q. So these points you need to understand. Fundamental question about electromagnetic induction, means about Faraday's law and Lenz's law. If you have understanding of these points, so we can write down your answer. So this is how you can write down your final answer. And so you can say current in wire P gives rise to magnetic field, means current in this wire produces its own magnetic field. As current in P changes, or you can say as current in P decreases, wire Q cuts magnetic flux of wire P. Cutting magnetic flux causes induced EMF across wire Q, or you can say changing magnetic flux causes induced EMF across wire Q. So this is how you can write down your answer. If you write down these points, you will get 3 marks. For the second part on figure 5.3, we need to sketch a line to suggest the variation with T of the voltmeter reading V. Means simply question is asking you how this voltmeter reading is changing with time. And this voltmeter reading is depending on current in wire P. And current in wire P, we have already discussed that this is changing exponentially with time. It is decreasing exponentially with time. So we can write down time here as well. Current in P is decreasing exponentially with time. So we can draw the graph like this. And this is decreasing exponentially. So we have current, this is equal to I naught e to the power of minus t over RC. Now we need to understand in this case how EMF is changing. EMF is equal to negative d phi by dt. And EMF is proportional to negative dB by dt. And magnetic field around this wire is proportional to current in wire P. So we can also say that EMF is proportional to negative di by dt. So this is the main point you need to understand. Negative di by dt means EMF is proportional to negative current gradient with time. negative. As the gradient of this one we can see is negative, and this gradient is decreasing with time, so the EMF has to be positive because EMF is negative of current gradient. So EMF will be positive and EMF will decrease with time. Actually, the shape of EMF and the shape of I against T graph will be the same, because if we have EX and we take the derivative of EX, they are the same. EX and the derivative of EX, they are the same. So this is equal to EX. So it means EX graph and the derivative of EX graph, they have the same shape, because derivative of EX is equal to EX. So if this point is clear to you, then simply you can draw the graph. So these two graphs, they should have the same shape. So simply we can sketch our graph for V here. So this is how V will change with time. So let me draw in a proper way. So we can draw a little bit in a proper way. So you can draw it is somewhat like this. But it should not touch T-axis, because this graph is also not touching T-axis. So when change in current is very small, EMF will be very small. So we can also say here, when current is changing very slowly with time, meaning the change in current is about equal to 0. So the EMF also will be about equal to 0, but EMF will not be 0. So that's the reason it should not touch T-axis. For question number 6, it is given to us figure 6.1 shows a thin slice of semiconducting material used in a Hall probe. Current I passes through the slice in the direction shown. The slice is placed in a uniform magnetic field of flux density V, so that two of its faces are perpendicular to the magnetic field. A steady Hall voltage is developed between the faces PQXY and phase SRYZ. For part A1, use the letters in figure 6.1 to identify the faces that are perpendicular to the magnetic field. Means we need to find out the faces which are perpendicular to the magnetic field. Perpendicular to the magnetic field. And so for this one, simply we can imagine, first of all, as this current is passing through this slice, imagine that there is a positive charge, and the force on this positive charge, in this case, if you can find out, then simply you can answer this question. But first of all, we also need to understand, it is given to us that Hall voltage is developed between these two faces. So it's developed between these two faces, PQXY, PQXY. So Hall voltage is developed between this phase, and Hall voltage is developed between SRYZ, between this phase. So it is developed between these two phases. So we can also imagine that this side become more positive. So just you can imagine. So this become more positive and this side become more negative. So it means in this case, magnetic force on the positive charge is to the left. So this is direction of magnetic force. Now simply you need to understand Fleming left-hand rule. Actually, this question is simply about Fleming left-hand rule. For Fleming left-hand rule, you need to understand current is perpendicular to magnetic field, meaning is at right angle to the magnetic field. Current is also at right angle to the magnetic force. And same is true for any. All of them, they are perpendicular to each other. So if this point is clear to you, then simply you can answer this question. So in this case, we have current, so that is into the page. So we can draw this is current, this is into the page. And we have magnetic force in this case. Magnetic force is to the left. So this is direction of the magnetic force. So magnetic force is to the left. Now you can find out direction of magnetic field. So we have said current in this case is into the page. I mean, this finger is pointing into the page, and the force, and you can see force is, let me draw like this. So in this case, you see the force is to the left, current is into the page, and the magnetic field is pointing down. Our magnetic field will be pointing up if this side is positive. If this side is positive, then magnetic field will be pointing up. Magnetic field will be pointing up. So let me write on the second situation. Current is into the page. If the magnetic force is to the right, so this will be easy for you to understand. So in this case, current is into the page, and the magnetic force, you can see, is to the right. So the magnetic field is pointing up, and vice versa is also true. If force is to the left. Force is to the left. So the magnetic field will be down. And so it means direction of the magnetic field is vertically up or vertically down. So the magnetic field is perpendicular to these two faces. So we can say this face, this top face, this face is perpendicular to this face, perpendicular to this face, and this face is PQRS. PQRS. So magnetic field is vertically down, or you can say is pointing vertically up. So it is perpendicular to PQRS. So you can say PQRS and WXYZ. So this is W, this is X, this is YZ. So magnetic field is perpendicular to these two faces. So let me explain in a better way. So you can imagine that this is the box. So magnetic field is like this. So it is perpendicular to this face and also perpendicular to this bottom face. So magnetic field is like this. Our magnetic field can be like this because we don't have exact direction of magnetic field, but magnetic field is along vertical. So if this point is clear to you, then this question is very straightforward one. You can look at this question, you can find out. So we can simply write down this will be W, X, Y, Z. For the second part, we need to explain how the steady Hall voltage is developed between phases PQ, XY and SR, Y, Z. Between phase PQ, XY, mean between this phase and this phase, how this is developed. You can also imagine in this case, if you connect a voltmeter here, you will read reading on voltmeter. And this voltmeter reading is the Hall voltage. Now we need to explain how this Hall voltage is developed. Steady Hall voltage. Steady means constant, means when it has reached maximum value, Hall voltage will be constant. So for this purpose, we need to understand initially when current will flow, imagine that there is a positive charge here. This positive charge will experience a magnetic force because in this case, the magnetic field is vertically downwards or is vertically upwards. So we can imagine in this case, magnetic field is vertically upwards. So I will draw just one arrow. Imagine that magnetic field is vertically upwards like this. It's vertically upward. If the magnetic field is vertically upwards and current is into the page, so the positive charge will experience force to the right. So positive charge will experience force to the right. So this side will be more positive. So this side will be more positive and this side will be more negative. Now I will simply clear this arrow now to show you the forces acting on this charge. So initially the force acting on this charge will be only magnetic force that will be acting this way. So this is the magnetic force. But as more and more positive charges accumulate on this side, there will be more negative on this side. So there will be electric field between these two faces. So there will be electric field from positive negative. So I will just draw these big arrows. So there will be electric field. So this is direction of electric field. Simply you can imagine just one arrow we have drawn. So this one arrow is telling you direction of electric field. So the electric field will be this way. So as electric field is pointing to the left, so this positive charge, it will experience electric force also to the left. And one stage will come after a very short period of time. We will see these two forces are equal. Electric force will balance magnetic force. So this one is the electric force. So let me use different color. So electric force. So this force is electrical force. After small amount of time, short amount of time, FB will be equal to FE, electric force. So when these two forces are equal, then current will just flow in a straight line. So it will just flow in a straight line. Means charges, they will not be deflected towards positive plate or towards negative plate. And at that point, this Hall voltage, this will have reached the maximum value, or we can say this Hall voltage will be constant, or you can say this will be steady, or you can say it has reached the maximum value. So you have to understand only these points. If you have this understanding now, then you can write down the answer. So let me show you the answer, how you can answer this problem. So in your answer, you can mention these points. Force on charge carriers is perpendicular to both magnetic field and current. We have already discussed, according to Fleming-Lefton rule, force has to be perpendicular to the magnetic field. Force also has has to be perpendicular to current. Very important point. Current has to be perpendicular to the force. Current also has to be perpendicular to the magnetic field. And this is also true for the magnetic field. Magnetic field perpendicular to current and also perpendicular to force. So very important point. In the last part, they were checking your understanding of this point. And next one, you can say as charge carriers are diffracted to one side and electric field is set up. As we have discussed, there is an electric field that is set up between these two faces. Steady VH when electric and magnetic forces on charge carriers are equal and opposite. Then charges just move in a straight line. So they will not diffract. Initially, they will diffract. So when they go, they will diffract one side because magnetic force is stronger. But as time will pass, electric field will also get stronger. When electric force is getting stronger, so there will be less and less net force on positive charges. And at one point, two forces will be balanced. So then charges will just go in a straight line. And at that point, value for voltage will be maximum. And that value is steady Hall voltage. For part D, it is given to us the magnitude of VH is given by the equation. Means VH is equal to Pi over NTQ. And for part D1, we need to state the meaning of the symbols N, T, and Q. You may refer to the letters in figure 6.1. So first of all is N. N is the number density of charge carriers, mean number of charge carriers per unit volume. So we can say this is number density of charge carriers. So this is one point you can write down. Number density of charge carriers. And T is the thickness. T is thickness. And this is thickness of the side through which magnetic field is passing. So magnetic field in this case is passing through PW. So we can say this is thickness PW, or you can say this is thickness SZ, or you can say RY, or you can say this is RY. Means the thickness through which magnetic field is passing. So in this case, magnetic field is vertically, so it is passing through this thickness. We can say this thickness. So this one is the T. And the last one is Q. Q is the charge on charge carriers. Charge on each charge carrier. So this is charge on each charge carrier. So if you write down these 3 points, you will get 3 marks. Now let's go to the second part. For the second part, we need to suggest with reference to the equation, mean we have to use this equation. Why the slice of the material used in a Hall voltage, Hall probe is thin. So for that purpose, simply you can understand, if we make T small, mean this T become small. So the VH will be large. So if the VH is large, so it is easy to measure. So that simply you need to write down. So we will say in this case, if T is smaller, means the slice is thinner, it means Hall voltage produced will be larger. So it will be easy to measure with higher accuracy and lower percentage uncertainty. With higher accuracy, simply you can say. So these points you have to mention. So let me show you the answer. So in your answer, so you can mention these points. So you can say simply in this case, VH is proportional to T. Actually, this is inversely proportional to T. So you can say VH is inversely, if you want to say in a proper way. So is inversely proportional to T. So T needs to be small for VH to be large enough to measure. So if T is small, VH will be large. So we can measure VH with a higher accuracy, or you can say with lower percentage uncertainty. So these points we have to mention. If you mention these points in your answer, you will get 2 marks. So this is also the answer for part A. Even if you write down VH is proportional to, that is acceptable because they are proportional, mean it is inversely or directly proportional. So, but if you want to be very specific, you can also say VH is inversely proportional to T. So if the T is small, VH will be larger. And if VH is larger, it means we can reduce percentage uncertainty, or we can measure this one with higher accuracy. And that's all for today's video. I hope you have some better understanding of these topics. And if you have any questions, please leave your questions in comments and I will be answering as soon as possible. Welcome to A-Level and AP Physics. In today's lesson, we will discuss past paper questions on AC, quantum physics, astronomy, and nuclear physics from October-November 2022, paper 4, variant 1. In the last video, we have discussed from question number 1 to question number 6 in the last two videos. And for the solution of those questions, you can go to the channel and you can search for October-November 2022, paper 4-1, part 01 and part 02. And in today's lesson, we will start from question number 7 and we will discuss questions from question 7 to question 10. And we will discuss these questions in detail as always we do. So you can improve your conceptual understanding of these topics and also you can have better understanding of these questions. Let's study together. Let's improve together. For question number 7, part A, it is given to us a sinusoidal alternating voltage as a root mean square, potential difference of 4.2 volts and a frequency of 50 kilohertz. For part A1, it is given to us the alternating voltage is applied across a resistor of resistance 760 ohms. By considering the peak voltage, we need to show that the maximum power dissipated by a resistor is equal to this one. So we need to calculate P. Question is asking you to calculate value of P. So P in DC circuit simply is equal to V squared divided by R. So simply you can write down the formula. Now question is asking you to calculate the maximum value of power dissipated. So this value has to be peak value. So this is how you can come from DC to AC. But in the question we have RMS. So this is VRMS. So we need to convert VRMS into peak value. So simply we can write down peak value. This one will be equal to root of 2 times VRMS. Root of 2 times VRMS. Simply most of the time students they just remember VRMS. So you can also write down VRMS is equal to V peak divided by root of 2. So from here you can go back to V peak. So we need to calculate value of V peak and we have value of VRMS. VRMS is equal to 4.2. Now if you multiply this one, you will get the answer that is equal to 5.9 volts. Now simply you need to plug in these values. And so the V peak is equal to 5.9 squared. Divided by, we have value of resistance that is equal to 760 ohms. Now, if we solve this one, our final answer will be equal to 0.046 watts. And we can convert this one into milliwatts. So simply we have this is 4.6 times 10 to minus 2 and we multiply this one with 1000. So our final answer will be equal to 46 milliwatts. So this is what we need to show. So this is our final answer. And so if you have done this one, in this case you will get 2 marks. For the second part on figure 7.1, we need to draw a smooth curve to show how the power dissipated in the resistor varies with time t. Between t is equal to 0 and t is equal to 40 microseconds. And also we need to assume that P is equal to 0 when T is equal to 0. For this question, frequency is given to us. We have value of frequency of alternating voltage. Frequency is equal to 50 kilohertz. So this is the frequency. So the time period we can calculate from here. Time period will be equal to 1 over frequency. So we have here 1 divided by 50 times we have 10 to 3. And if we solve this one, in this case we will get 2 times 10 to minus 5 seconds. But the given unit is microseconds. So we have to convert this one into microseconds. So we have to multiply this one by 10 to 6. Now if we solve this one, we will get 20 microseconds. So this is the time period. Mean the time period of alternating voltage is 20 microseconds. And the time for power, this will be half of that. So it means this is the time period for alternating voltage and the time period for P power repetition, that will be half of that. So that will be 10. So here this is 10. So here it is 10. So means 4 half cycles you have to draw. So in this case, total power was given to us, power dissipated in the resistor. P max was given to us. We have just calculated that is equal to 46 46 milliwatts. 46 milliwatts. Now, if you look at the given scale, we have 0 to 25 and we have 10 small square. So one small square, we can say in this case, one small square is equal to 2.5 milliwatts. So this one is 50. So this will be 47.5 and this will be 45. So the 46 will be a little higher than 45. And also we need to understand the peak will be at the half. So you have 1, 2, 3, 4, 5. So the one peak will be here at this point. And we can also count 5 here. 1, 2, 3, 4, 5. So the peak will be here. We can also count here 5. 1, 2, 3, 4, 5. So the peak will be little above 45. And here 1, 2, 3, 4, 5. So peak will be here. Now simply we need to draw 4, in this case, half cycles. So this is how you can draw. Look at this one. This is in a nicer way you can draw. So this is how you can draw, and the shape should look like this one. So you can see we have drawn these 4 cycles. Actually, for alternating voltage, this is one complete cycle, and this is the time period we have calculated, and the power is the half. So it is repeating because power is I square. So that's the reason this negative side, this flip. So we have 4 here. So if you draw like this, you will get 3 marks for this question. And this is a typical type of question. So you have to be clear about this one. How to sketch power against time. For our third part, we need to use our graph from A2, and we need to explain why the mean power dissipated in the resistor is 23 milliwatts. Maximum power dissipated in the resistor we have just calculated, that was equal to 46 milliwatt. Now we need to explain why the mean power is equal to 23 milliwatts using this graph, means using this sketch. If you look at this sketch, this is not accurate sketch. This is just a rough sketch, and this one is accurate one. So I will explain you with the help of this. So in this case, we have the graph I square against time. So the power in this case will be equal to I naught squared times R. So this one is the maximum power, and power, mean power from here, this one will be equal to I naught squared times R divided by 2. So this is the mean power. Mean power means that is certain value of the power that is always across the resistor, because the power is changing. You can see that power is changing between 0 and 46. So question is asking you what is the average value for this one. So the average value we can calculate. So if we divide this one into 2 parts from here, if you cut this one and you take this part and you place this one here, so you see this is part. So we can place this part here, and if we cut this part here, this will be at this point. So you can see now the power is just a horizontal line, and this is 23 milliwatts. And the same you can do for this one. You can cut this one here and you can fit here, and this part you can fit here. So in this case, the average power dissipated in the resistor is equal to 23 milliwatts. Question is asking us to explain with the help of the graph. So simply we can say in this case the line is symmetrical about 23 milliwatts. Mean this is the power that is always dissipated in the resistor. So this will be here, and if you cut this one, for example, this part you can fit here, and this part you can fit here, and so on. So this part you fit here, this part here. So the power dissipated, average power dissipated across resistor is equal to 23 milliwatts. So if you look at this sketch, in this case 23 will be, this is 25, and this one will be 22.5. So 23 will be around here, about here. So it is symmetrical about this part, symmetrical. So simply you can say in this case line is symmetrical about 23 milliwatts. If you write on this point, you will get 1 mark, and that is the B mark. So this mark will be B mark. For part B, it is given to us the alternating voltage in A is now applied to a piezoelectric crystal in air. For part B1, we need to explain what happens to the air surrounding the crystal. But one thing we need to understand is that frequency of alternating voltage is 50 kilohertz. This frequency was given to us in part A, and this frequency is in ultrasound range. So first of all, we can write down this is in ultrasound range. This frequency is in ultrasound range. Now we need to understand if we apply alternating voltage with this frequency, across the piezoelectric crystal. So this is our piezoelectric crystal. This one is the crystal. And now if we apply alternating voltage across this one, what will happen to this crystal? When we apply alternating voltage across this crystal will vibrate like this. So it will be compressed and it will expand, compressed, expand, compressed, expand. So it will be compressed and it will expand like this. So the surrounding air also will be compressed with the same frequency, and it also will expand with the same frequency. So the air surrounding also will be compressed, and also it will expand at the same frequency as frequency of alternating voltage, because crystal is vibrating at the same frequency. So in this case, we will say first thing, alternating voltage will cause the crystal to vibrate. So the crystal will vibrate, and when this crystal will vibrate, crystal will cause air to vibrate, means the surrounding air vibrate. Surrounding air will vibrate, and surrounding air will vibrate at a frequency in ultrasound range. So these 3 points you need to understand. If you write down these 3 points, you will get 3 B marks. So that's all. First of all, when you apply alternating voltage, crystal will vibrate. And when object is vibrating, vibrating objects produce sound waves. And the frequency of sound waves and frequency of vibration of the crystal will be the same as frequency of alternating voltage. So these points you need to understand. So if you have understanding of this one, so in this case, we can write down our answer like this. So these 3 points you can mention in your answer. You can say alternating PD makes the crystal to vibrate, and the vibrations of the crystal cause air to vibrate, and air is vibrating with this frequency. That is the frequency of alternating voltage. And so these 3 points you have to mention. So in this case, actually, we are producing ultrasound waves. So this one is acting like a transmitter. So very important thing you need to understand. In this case, crystal is acting like a transmitter, means producing ultrasound waves. But this crystal can also act like detector. So that one we will see in the next part. For the second part, it is given to us a second piezoelectric crystal is placed in the air near to the first crystal. Explain the effect of the surrounding air in B1 on the second crystal. In the first case, we have seen crystal is vibrating. So you can look at this one. This crystal is vibrating. So this is our first crystal, vibrating crystal. So this is the first one. So this is first crystal. And this one you can imagine, this one is second crystal. So this one is second crystal. Now in this case, first crystal is vibrating due to the applied voltage. So as first crystal is vibrating due to applied voltage, there will be sound waves. So this is producing sound waves. Then when these sound waves, they will hit this piezoelectric crystal. This piezoelectric crystal will be compressed, and this piezoelectric crystal will expand. Because when compression is coming, this will be compressed, and when wave fraction is coming, this will expand. So this crystal will be compressed and this will expand. So in this case, one side of this crystal be more positive, one side will be more negative, and this process will repeat. Means first time this become more positive, this will be more negative, and then when wave fraction come, this will be more negative, just imagine, and this will be more positive, and so on. So in this case, there will be alternating voltage across this second crystal. So if we connect our voltmeter here, we will see alternating voltage on this voltmeter. So simply this vibrating air will cause, or we can simply say will induce EMF across this piezoelectric crystal, across the second. Now in this case, this one is acting like a detector. So this second crystal is acting like a detector, and the first one is acting like a transmitter. And this is very important for ultrasound. So you have to be very clear about this one. So the first crystal is acting like a transmitter, and second crystal is acting like a detector. That's reason in ultrasound probe, we only use one piezoelectric crystal that acts like a transmitter. Then same crystal also acts like detector. And for this question, just 1 mark. So if you write down this point, you will get 1 mark. and that is prima. Air makes crystal to vibrate, which causes an EMF to be generated across the second crystal, and you will get 1B mark. And this question was conceptual question, not difficult one, but little bit tricky one, because most of the time students, they just try to memorize how ultrasound waves are produced, but they don't understand the whole process. They don't understand the reasoning behind that, or we can say the concept behind that, how ultrasound waves are produced and what is happening to the air surrounding the crystal. So this was conceptual question, and many students, they got confused with this one. They were not clear what to write for this answer. For question number 8, part A, we need to state what is meant by the work function energy of a metal. Work function energy of a metal, simply we can understand with the help of simple diagram. Imagine that we have, this is a piece of metal. So this is piece of metal. It has many electrons. Some electrons, they are at the surface. They are close to the surface. So these are electrons close to the surface. And now if electromagnetic radiation is coming, let's say energy of this electromagnetic radiation, we can also imagine this is a photon. Imagine that this is a photon of EM radiation is coming, and frequency of this one is F. Now we can write down photoelectric effect equation. According to photoelectric effect equation, energy of the photon, this is equal to kinetic energy maximum plus work function. Now in this case, if kinetic energy maximum is equal to 0, then we can say energy of the photon is equal to the work function, and that amount of energy we need, the minimum amount of energy we need to release electron from the surface of the metal with 0 kinetic energy, that minimum energy we call is work function. So we can also say HF naught. So this frequency we also call is threshold frequency. So F naught in this case is representing threshold frequency. So this is threshold frequency. So next time they can ask you about what is threshold frequency. So this is threshold frequency, means the minimum frequency required, minimum frequency of electromagnetic radiation required to release electron from the surface of the metal with 0 kinetic energy. So you can also define threshold frequency. So in this case, when this electron will be released from this metal, it will sit here, but its kinetic energy will be equal to 0. So that energy of electromagnetic radiation is equal to work function of the metal. If energy is greater than work function of the metal, then electron will have some kinetic energy. So this is how you can write on your answer. So in the answer, you have to mention minimum is very important. Minimum photon energy required to remove electron from metal surface with 0 kinetic energy. This question has 2 marks. So if you have written first part, minimum photon energy required to remove electron from metal surface, you will get 1. And if you have mentioned about 0 kinetic energy, you will get the second mark. This is a typical question. So you need to understand how to write down work function energy. You also need to understand how to state threshold frequency. For part B, it is given to us ultraviolet radiation of frequency 1.36 times 10 to 15 Hz is incident in a vacuum on a metal surface. The power of radiation incident on the surface is this. Photoelectrons are emitted with a maximum kinetic energy of this one. Determine the number of photons incident on the surface per unit time. Very nice question. Number of photons incident on the surface per unit time. So in this case, we have the power. So the power is given to us, and power is equal to energy over time. So power is equal to energy over time. So in this case, we need to find energy per unit time. So simply you can say energy is representing the total energy. So this is the total energy. So I'll be using for this one total energy for better understanding. So this is the total energy falling on the surface of the metal per unit time. So we can say total energy per unit time. So this one is unit time, means 1 second. So we can also write down per unit time. Total energy per unit time. Per unit time means 1 second. Total energy means that this is equal to number of photons reaching the surface times energy of single photon. So we will be writing this multiplied with energy of single photon. So I'll be just writing HF because this is representing energy of single photon. Divided by unit time means 1 second. So I'll be writing here, this is 1 second. Now from here, N you need to find out, and value of HF. So this is HF. So simply P, now you can simply see NHF, because this is 1 second. So we need to find out value of N. So N simply will be equal to P divided by HF. So N is the number of photons per second. So power is given to us, power is 8.36 milliwatts. So this is 10 to minus 3 divided by H is the Planck's constant, and Planck's constant is equal to 6.63 times 10 to minus 34 joules second. And in this case, we have frequency of incident light, that is 1.36 times 10 to 50. Now, if we solve this one, we will get our final answer, that will be equal to 9.27 times 10 to 15. I mean, this number of photons are reaching the surface in 1 second. So you can simply write down, this is 9.27 times 10 to 15 after 3SF. Why we are using 3SF? Because given data, this one has 3SF, this has 3SF, this also has 3SF. So you have to use at least 3SF in your final answer. For the second part, we need to calculate the work function energy of the metal. Work function energy of the metal, and we have frequency of electromagnetic radiation, and also we have the maximum kinetic energy of photoelectrons. So simply you have to use photoelectric effect equation. Photoelectric effect equation means HF, this one is equal to kinetic energy maximum plus work function, and this is energy of the photon, energy of incident photon. In this case, we need to calculate work function. So this is the work function. So work function simply is equal to HF minus K max, kinetic energy maximum of photoelectron. So we have in this case H, that is equal to 6.63 times 10 to minus 34, and we have frequency of incident radiation, that is equal to 1.36 times 10 to 15 minus kinetic energy maximum. This kinetic energy is given in joules, so simply we can use this one. If this was given in electron volts, so you have to convert into joules. So simply in this case we can write down, this is 3.09 times 10 to negative 19. Now if we solve, our final answer in this case will be equal to 5.93 times 10 to minus 19 joules, and our answer has to be up to 3SF. Because the given data, we have 3SF here, we have also 3SF here. So you can see 3SF. So this is our final answer. So simply we can say this is 5.93 times 10 to minus 19 joules. And if you have done this one, you will get 2 marks. Typical question. So this equation is very important for photoelectric effect. If any question you are not clear, write down this equation and you will be able to figure out the answer. For part C, it is given to us the frequency of the radiation incident on the surface in B is increased while the power remains constant. State and explain the effect of this change on the maximum kinetic energy of the photoelectrons. Pretty straightforward question. In this case, power is kept constant, but energy of each photon has been increased. So simply we can understand from here, we have discussed this point already. Power is equal to the total energy of electromagnetic radiation divided by time. So this is time. So total energy is equal to number of photons times energy of each photon divided by time. So in this case, it is given to us that frequency has been increased. If we consider the same amount of time, number of photons have to decrease because power is kept constant. So in this case, frequency of each photon has been increased. If frequency of the photon increase, it means energy of the photon has been increased. And we need to compare that one with maximum kinetic energy. Means what is the effect on maximum kinetic energy? But work function of the metal in this case is also is constant. We're using the same metal. So simply you have to write on photoelectric effect equation. So we can write on HF, this is equal to Kmax times work function. So Kmax, we can make the subject. So the Kmax is equal to HF minus work function. So simply you can see from here now, if the frequency increase, it means this energy increase. So the Kmax also increases because we are using same metal. So work function is the same. So that's all simply you need to understand. So you will say greater photon energy, same work function. Greater photon energy, same work function, so higher maximum kinetic energy. So let me show you the answer, how you can write. So these points you can mention in your answer and you will get 2 marks. So you will get 1 mark for writing greater photon energy and same work function. Second point, because it's asking you state. So this is a statement, maximum kinetic energy increases. You will get 1 mark for this one, 1 mark for the explanation, because this is your statement. So this is your statement. And this one is explanation. So this is how these 2 marks will be awarded. For the second part, we need to state and we need to explain the effect on rate of emission of photoelectrons. But in part 1, we have already discussed that power is equal to NHF divided by time. As the frequency of electromagnetic radiation increases, so the number of photons decreases. And number of photons is linked with number of photoelectrons. So simply we can say number of photons. This is linked with number of photoelectrons. So this is linked with number of photoelectrons. Because interaction between photon and electron is one-to-one interaction. So in this case, if this go down, this will also go down, because you can also, in a better way, you can say they are proportional. So we can use the sign of proportionality. They are proportional to each other. If the number of photons go down, so number of photoelectrons also will go down. So the rate of emission, so then we can say rate of emission in this case will decrease. Rate of emission decreases. If you have this much understanding, now we can write down our answer. In the answer, you can mention these points. So first you can say greater photon energy, same power, so lower number of photons per unit time. Each electron absorbs only 1 photon, so lower rate of emission. So this one is the statement, and the above one is the explanation. So this is the statement and this is the explanation. So if you write down these points, you will get 2 marks. And that's all for today's video. And in this video, we have talked about AC, alternating current. We have talked about quantum physics. I hope these questions are clear to you, and also you have better understanding of these 2 topics. If you found this video helpful, means if this video was helpful and this video helped you to improve your conceptual understanding and also give you better explanation of these questions, then please like and subscribe, because your encouragement is very important. And remaining 2 questions I will be solving very soon, maybe by today or by tomorrow morning. See you in next video. Welcome to A-Level and EP Physics. In today's lesson, we will discuss past paper questions on astronomy and nuclear physics from October-November 2022, paper 4, variant 1. In the last videos, we have discussed questions from question number 1 to question 8. And today's lesson, we will focus on question number 9 and question number 10. And for the solution of first 8 questions, you can go to the channel and you can search for October-November 2022, paper 4, variant 1. And you will find a detailed solution of first 8 questions. And understanding of those questions is very important, because those questions are based on new syllabus. And in today's lesson, as always we do, we will discuss these questions in detail, so you can improve your conceptual understanding of these topics, and also you can have better understanding of these questions. Let's study together, let's improve together. For question number 9, part A, we need to state what is meant by the luminosity of a star. And luminosity of a star is the total amount of energy radiated by a star per second. Or simply we can say luminosity is equal to power of radiation, total power of radiations. So this is what we call is luminosity of a star, power of radiations. Now in this case, if you look at this figure, so here we have a beautiful star. So the luminosity of the star means that total amount of energy radiated by this star per second. So that one is the luminosity. So simply we can say for the luminosity is the total power of radiations emitted by the star. And this question is a typical question. It's possible if there is any question about astronomy in your final exam, you will see this in your exam. I mean, they will ask you to state what is luminosity of a star. So you have to be very clear what is luminosity of a star. And let's move on to part B. For part B, it is given to us a star in the constellation Canis Major is a distance of 8.14 times 10 to 16 meters from the Earth and has a luminosity of this one. The surface temperature of the star is given. Calculate the radiant flux intensity of the radiation from the star observed from the Earth. Give a unit with your answer. So question is simply asking us about intensity. Radiant flux intensity. It simply means that this is the intensity. And in this case, we need to write down what is intensity. Intensity simply is equal to F, and F is equal to L divided by 4 pi d square. And we have the value of luminosity. So this is value of luminosity. Luminosity is equal to 9.86 times 10 to 27. And this is divided by 4 pi d square. D is the distance. So we have here distance is given. That is 8.14 times 10 to 16 square. And now if we solve this one, we can find out value of radiant flux intensity. But question is also asking us to write down the unit. So the unit of luminosity is watt and unit of distance is meter square. So the unit of this one will be watt per meter square. So this is the unit. Now before we write down the final answer, let me explain you the difference between radiant flux intensity and the luminosity. Radiant flux intensity and luminosity. Let's try to understand the difference between these two with the help of this figure. So luminosity is the total power radiated by the star per second, and intensity at any distance. For example, at this point we can calculate value of the intensity. This is the amount of energy per second reaching this unit area. That one is the intensity, means power per unit area. So reaching at this point, that is intensity. And intensity we need to understand. It depends on distance. So the intensity of the star at this point, let's say this is point A and this is point B. Intensity at point A and intensity at point B will be different because intensity depends on distance from the star. But luminosity is intrinsic property of a star and it does not depend on distance. So you have to be very clear about this point. Let's try to understand a little bit more about intensity. Why intensity decreases with distance? The reason is that amount of energy produced by the star per second is constant. I mean, luminosity of a star is the intrinsic property of a star. So we are assuming that is constant. But intensity depends on the distance. So it simply means that the same amount of energy is spreading over larger and larger area. So as energy is spreading over larger and larger area, so it means that energy per unit area will decrease. So that's the reason intensity decreases. So first of all, you can imagine that energy is concentrated at single point, then energy is concentrated at this much area, then at this much area, then at this much area, then energy is spread it over this area, then this big area, then that big, very large area. So it means intensity will decrease, energy per unit area is decreasing because same amount of energy is spreading over larger and larger area. So you must have this sense. Now simply just remember the formula. Radiant flux intensity is luminosity over 4 pi d square. So you must have sense about this one. So you can get feelings about physics. So you can understand these quantities. Now let's try to write down our final answer. And so simply if you use calculator and you calculate these values, your final answer should be equal to 1.18 times 10 to minus 7. So this is intensity, 1.18 times 10 to minus 7. Now the question is that why we're using 3SF? Because in the given data you can see this one has 3SF, least number of SF. This one also has 3SF. So least number of SF in the given data is 3SF. So in the final answer we are also using 3SF. So if you do this one, you will get 2 marks. For the second part, we need to determine the radius of the star. So we have temperature of the star, surface temperature of the star, and we have luminosity of the star. We can use these two quantities and we can determine the radius of the star. So you can see how beautiful physics is. Our physics make our life easier. So we are just sitting on our planet, we have the luminosity, we have surface temperature, we have determined using other methods, and now we can find the size of the star. So for this purpose, simply we have to use Stephen-Boltzmann law. According to Stephen-Boltzmann law, luminosity is equal to 4 pi sigma, this is Boltzmann constant, times r squared, this is radius of the star, times T to the power of 4. And this is thermodynamic temperature, means temperature has to be in kelvins. Now simply we need to find out value of R. We can plug in values and we can find out value of R. Otherwise you can also rearrange this one. We can write down in this case R squared, this will be equal to luminosity, divided by 4 pi, we have sigma, and here we have T to the power of 4. So we need to find out radius in this case. We need to find out radius, so we can take square root on both sides. Square root means the power of this one is 1 by 2. And now simply we need to plug in values. The value of luminosity we have, that is equal to 9.86 times 10 to 27. This value we have, this was given to us in the last part, and we have 4 pi, so here is 4 pi, and we have value of Planck's constant, that is equal to this is Stephen-Boltzmann constant, not Planck's constant. So this is Stephen-Boltzmann constant, its value is 5.67 times 10 to minus 8. Then we have temperature that was given to us in kelvins, 9830 to the power of 4, and then we need to take square root of this one, 1 by 2. If we solve this one, our final answer will be equal to 1.22 times 10 to 9 meters. So this is the radius of the star, and this is how we can calculate. So simply we can say this is 1.22 times 10 to 9. And this question has 2 marks. If you have written Stephen-Boltzmann law, you will get 1 mark C1, and if you got the right answer, you will get answer mark means A1. And again, we are using theory SF here, because in the given data, least number of SF is equal to theory SF. So we have to use theory SF in the final answer. Part C says, explain how the surface temperature of a distant star may be determined from the wavelength spectrum of the light from the star. So wavelength spectrum simply means that you can see here, this one is the wavelength spectrum. We have wavelength on x-axis and we have the flux, means the intensity, on y-axis. So if this spectrum of a star we have, so how we can determine the surface temperature of that star? For that purpose, we need to understand Wien's displacement law. Wien's displacement law. Let's say if we look at this star here, so we can find out its peak wavelength. We can find out lambda peak. So we can say lambda peak, according to Wien's displacement law, lambda peak times surface temperature in kelvins. This surface temperature has to be in Kelvin. This is equal to constant. So this one is equal to constant. It simply means that this is true for any star. So simply we can say then lambda peak, I will say lambda 1 times T1 for one object if we have. So then for the second object, let's say this is lambda 2, and we need to find out T2. If we have lambda 1 peak wavelength of one star, and we have its surface temperature in kelvins, and we have its wavelength, and we need to find out surface temperature of the second star. And so in this case, simply surface temperature of the second star will be equal to lambda 1 T1 divided by lambda 2. So we can find out surface temperature of another star. If we have lambda peak and thermodynamic temperature, means surface temperature in Kelvin, and we have the wavelength spectrum of a star, so we can determine the wavelength of that star. So this is simply how you can use Wien's displacement law. If you have the wavelength spectrum, I mean if you have this spectrum, from this spectrum first of all you will find value of lambda peak. When you have value of lambda peak, then you can look for another object, or you can look for another star which has known value of lambda peak and known value of surface temperature, and then you can use Wien's displacement law and you can find out value of surface temperature of unknown star. So this is how we use Wien's displacement law. So how to write down the answer? So let me show you the answer, how you can write down your answer. So in this case, you can write down wavelength of peak intensity determined from the spectrum of the star. So this is step 1. So step 1, when the wavelength spectrum is given to you, you can determine the peak wavelength. So we can say this is step 1. You can determine this one from the given wavelength spectrum. And wavelength of peak intensity from object of known temperature determined. So if you have another star, for example, so just imagine that we have this red one. we have value of its peak wavelength, and also we have its surface temperature. Then what we need to do is simply we need to use this ratio, means displacement law, and we can find value of surface temperature. So you can say using wind displacement law, we can determine surface temperature of a distant star. So these 3 points you have to write down. If you write down these 3 points, you will get 3 marks. And these are B marks. Question 10 says carbon-15 is an isotope of carbon that undergoes radioactive decay to nitrogen-15, which is a stable isotope of nitrogen. Radioactive decay is both a random and a spontaneous process. State what is meant by random and what is meant by spontaneous. These two terms are very important for your exam, so you need to understand how to state these two terms in a proper way. First of all, let's try to understand what is random. For random, we can imagine that we have a sample, and this sample, imagine that it consists of 4 atoms, or simply you can say 4 nuclei. So this sample consists of 4 and 4 nuclei. Means it consists of total 8 nuclei. And random means that we understand after one half-life, half of them they will decay into an other element. But we cannot predict in this case when this one particular nucleus will decay. So that is random. Means it cannot be predicted when a particular nucleus will decay. So it cannot be predicted. So this is what is meant by random. Now let's try to understand spontaneous. Spontaneous means that radioactive decay is independent of temperature, is independent of pressure, and also independent of neighboring nuclei. So when the time will come, it will just decay. Means radioactive decay will happen. But we cannot accelerate this one by increasing surrounding temperature or by increasing pressure or by neighboring nuclei. So this is what is meant by spontaneous. I hope this is clear to you. Let's try to write down the answers. In your answer, you can mention these points. In your answer, you can write down cannot predict when a particular nucleus will decay. You can also say for spontaneous, it is not affected by external factors such as temperature, pressure, or neighboring nuclei. So if you write down these 2 points, you will get 2 marks. Part B says a small sample of carbon-15 decays. The mass capital M of carbon-15 in the sample decreases with time t. Figure 10.1 shows the variation with time t of the value of ln m. For part B1, we need to state how figure 10.1 demonstrates that radioactive decay is random. If you look at this figure, and this line you can see is fluctuating. There are fluctuations in this line. It means that the radioactive decay is fluctuating. So it means radioactive decay is random. And we can see this one from the line because the line is fluctuating. So simply you can say as line fluctuates, it means this decay means the radioactive decay is random process. For the second part on figure 10.1, we need to draw a straight line of best fit. So simply you need to draw a straight line of best fit. So let me show you how you can draw. So this is how you can draw best fit line. This has to fit this zigzag line. So the same number of points above, same number of points below. So this is how you can draw the best fit line. For third part, we need to show that decay constant of carbon-15 is given by the magnitude of the gradient of line in P2. And this is the line we have sketched in P2. Now we need to show that magnitude of the gradient of this line is equal to decay constant. And if you look at y-axis, we have ln m on y-axis and we have time on x-axis. In order to answer this question, simply we can start with nuclear decay equation. N is equal to n naught e to the power of minus lambda t. And this is exponential decay equation. Same type of equation we also use in discharging of capacitor, because discharging of capacitor and nuclear decay, they follow exponential decay. So we can use the same equation but with different quantities for capacitor, and also we can use for radioactive decay. And this equation is also given in the formula list. But here we have mass. How mass is linked with number of nuclei. Number of nuclei and mass, they are proportional to each other. If we have more number of nuclei, it means mass will be greater. So simply we can replace n with m. So we have m is equal to m naught e to the power of minus lambda t. Now simply we need to take natural log on both sides. So ln m, this will be equal to ln m naught minus lambda t. Now, if we rearrange this one, we can say ln m. This will be equal to minus lambda t plus we have ln m naught. If we compare this one with straight line equation, y is equal to mx plus c. In this case, we can simply say gradient is equal to minus lambda, negative lambda. So we can say gradient is equal to minus lambda. But question is asking us to find out magnitude of gradient. Magnitude of gradient. We need to show that magnitude of gradient means we don't need to worry about the sign. Magnitude of gradient, simply this is equal to lambda, and lambda is the decay constant. This is what we need to show, means magnitude of the gradient is equal to decay constant, and this question has only 1 mark. So simply you need to understand how to write down radioactive decay equation in linear form, and this question is very popular in 2022 and also in 2023. So you have to be very clear how to write down radioactive decay equation in linear form. So get familiar with this. For part 4, we need to use overlying in to determine lambda, and also need to give a unit with our answer. In the last part, we have this that gradient is equal to negative lambda. Now we need to determine the value of lambda. So we can write down lambda is equal to negative of gradient. Negative gradient. So in this case, we can say lambda, this is equal to negative. We can take this out and we can write down the gradient here. So in this case, I'll be taking these 2 points, 1 point here and 1 point here. You can take any 2 points on the line you have drawn. So I'll be taking these 2 points. So for this one, we write down delta y by delta x. So this is our value of delta y, and this is also value of delta y. And this is negative 4.8. We have value of t that is 0, and we have value of t that is equal to 11.6. So simply we can say in this case minus 8 minus into minus, be careful with these negative signs, 4.8 divided by 11.6 minus 0. Now if we solve this one, our answer up to 2SF, it will be equal to 0.28 per second. Rate of decay constant is per second, so this is per second. So our final answer up to 2SF is 0.28. So this is how you can calculate gradient, but you have to be careful with negative signs. If you don't use this negative sign here, you will get negative answer, but lambda cannot be negative. For part 5, we need to use our answer from B4 to calculate the half-life of carbon 15. So we have already determined value of decay constant, so simply we can say in this case half-life, this will be equal to ln 2 divided by decay constant. Ln 2 is equal to 0.693 divided by, you can use calculator, you will get this number, divided by decay constant. Decay constant is equal to 0.28. Now if we solve this one, our final answer up to SF will be equal to 2.5 seconds. So this is our final answer. If you got right answer, you will get 1 mark, and this mark is only for answer. Part C says the equation for the decay of carbon 15 can be written as. Statement explains how the mass of the products of the decay must compare with the mass of the carbon 15 nucleus. So this is our reactants and these are our products. We need to compare the mass of the products with mass of reactants. So in this case, simply we need to understand is that if this reaction is energetically possible, this is energetically possible. Energetically possible. So in this case, energy will be released. So simply we can say energy released. If energy is released, it means mass is decreasing. As energy is released, it means it is decreasing mass. Decreasing mass. So the mass of the product, daughter products, will be lower than the parent nucleus. Mass decreases, we can say. So we say mass decreases. Because decreasing mass has been converted into energy. Energy released in this nuclear reaction. Then energy released we can also calculate with the help of this one. Delta E is equal to delta mc square. And this is the mass defect. Mass defect means a decrease in mass. So the mass of daughter products has to be lower than the mass of parent nucleus. So that's all what you need to understand. So let me show you the answer, how you can write down the answer. In your answer, you can mention these points. This question has 2 marks. 1 for reaction to occur, energy is released. Any reaction which is energetically possible, energy must be released. Otherwise, energy has to be absorbed. And so this is energetically possible, so it means energy is released. Energy release comes from decreasing mass. So total mass of products must be less than mass of carbon 15, means the mass of parent nucleus. And this is end of this paper, end of this question, and also end of this paper. I hope you have better understanding of these topics and also you have better understanding of this paper. I'll see you next video.